Let's talk about stability. Now, this chapter that we're in, chapter 8, has several discussions of how to solve differential equations, but it also has discussions of different properties of differential equations and the systems that are described by those differential equations. Okay? So one of those properties is stability. One of the key important properties is stability, and it is about stability we will talk about today. Well, among other things. It's the first thing we're going to talk about. So, there we go. Found it. So, for a state model, which we're very, very familiar with nowadays, with A, B, C, and D matrices, constants, the system is in equilibrium. So here's a little definition, and you know that because it's in green. Equilibrium if all derivatives of the state vector, so the first derivative, time derivatives, because that's usually the only thing we take the derivative of the state vector with respect to, so x dot, x double dot, third time derivative, etc. All of them are 0. So it's in equilibrium if all of those derivatives of a state vector are 0. So what would that mean if your states were like the position and velocity of a mass? If those were your two state variables, what would it mean for it to be in equilibrium?
Not moving.
So yeah,
So
it's velocity, it's acceleration, it's jerk. Yeah, all of that stuff are all those derivatives are all equal to 0. So that is a fully equilibrium system. So it's not just that it's not moving, because, for instance, we've all heard that from our physics teacher. If you toss a ball up in the air and it reaches a peak, its velocity at that peak is 0, right? But its acceleration is non-zero. But that is not an equilibrium point.
Nope.
You're just gonna
Right?
fall back down.
Because it's still accelerating, and so that second derivative is non-zero. So equilibrium is like very, very stopped. Okay, very much not moving.
It's not moving. It's not gonna
It
move.
means like no forces.
It doesn't necessarily mean that, because you could have forces that are all
Zero.
canceling out,
Zero.
right?
Yeah.
Yeah. The acceleration has to be 0, but the forces don't have to be. You could have a statics situation, right? Because in statics, some of the forces always equal 0.
And some of the moments, don't forget the moments.
Yeah, you're right. You're right. We don't want to disenfranchise the moments. So,
Thank you.
in the absence of an input, so I'm going to do some of the good old writing now. In the absence, I just realized that my beautiful face isn't showing. Should fix that. Look at that. This lecture is going to be so much better now. Okay. In the absence
It was in the video of myself watching.
of an input, our state equation becomes x dot equals ax plus bu is what it typically is, right? Ax plus bu. But if I said in the absence of an input, u is 0, so we can get rid of that part of the equation.
Wait, why did you do? Oh, absent.
In the absence of an input, this is true. And it implies that it has an equilibrium of, so the left-hand side is x dot, so that's got to be 0, right? So 0 equals a x, right? And we're going to call this specifically x sub 0 so that we can keep that accounted for. And this implies, so you may not know this is in linear algebra, is required a little bit to recognize this, but that x0 must be equal to the 0 vector. And that's not true for all A matrices, for all matrices that happen to multiply a vector and equal 0, okay? But our A matrix is always going to have what's called full rank, okay? You'll learn what that means. And it means that you can invert it. It's an invertible matrix. It's square. It's invertible. And we can solve for x naught, and it would just be equal to 0. Okay. So that is what happens in the absence of an input. If the state is perturbed from an equilibrium, x naught, by an external influence, the response, x of t, can do one of three things. Okay? 1, can asymptotically return to x naught. So we call this asymptotically stable. I'm going to give you this a green thing. Asymptotically stable. So that's one possibility. What do we mean by asymptotically stable?
It approaches, it doesn't approach it. But
It
it's
approaches
stable.
it as an asymptote. So it's approaching, so meaning that it returns to x naught as an asymptote, right? So that's
It stays stable that way.
and so that we call that stable. So we say that's by definition stable. If it returns, if we perturb it from that equilibrium and we let it go, and it returns to equilibrium, even if it doesn't actually reach equilibrium, it's returning asymptotically. Like, for instance, the temperature response, the first order response, or an RC filter response, that capacitor is going to charge up, and it's going to decay to the final voltage, but it's technically, mathematically, never going to reach it, but it's going to asymptotically approach it. In the limit, it'll approach it. Similarly, as long as we approach that original equilibrium, then the system is stable, asymptotically stable. Okay. Another possibility is that we diverge. So we could go away, like fly off to infinity or something. And if that happens, then that's what we call an unstable system. Unstable. And finally, finally, the third possibility is that the state remains perturbed. So, like, for instance, if you had a state vector and you like bumped it over a little bit to a different state, it stays right there. It doesn't go back. It doesn't fly off. It just stays right there. Or it oscillates with a constant amplitude. So it could, like, you could perturb it a little bit and it might start oscillating, but it doesn't oscillate and approach equilibrium again. It oscillates and just stays at the constant amplitude. It also doesn't oscillate and get bigger and bigger with each swing past, right?
Right.
So that is a what we call a neutrally stable or a marginally stable system. So neutrally or marginally stable. system. So the following illustration demonstrates these concepts. So you can think of, as long as you think of this, I mean, this is just an illustration. It's not a really great thing in some regards, but it's a very common way to demonstrate this. So I'll do it. If you think of a world that has friction in it, and you make this your system, this gives you an idea of what asymptotic stability would be like. So say we were to look at the position of this ball as the state, and you would find that this is an equilibrium position right here. Okay? So if you stuck the ball right there at that equilibrium, nothing would change. If you perturb it from that equilibrium position, and you let it go, what is it going to do? Yeah, it's just going to go back and forth, just go over here, and then go over here, and go over here. But its amplitude's going to get smaller and smaller, right? Because we said there's friction. So it's going to get smaller and smaller, and it'll approach this equilibrium again, right? A marginally stable system, if you perturb it a little bit, it's just going to stay there, right? Nothing's going to happen to it. This doesn't give you the oscillation demonstration at all. So don't think in terms of oscillation for that little illustration. It doesn't work. But if you perturb it, it's just going to stay there. An unstable system, if you perturb this just a little bit, it's going to just fly right off that way, right? Or if you perturb it this way, it'll just fly right off that way. It's not going to come back. So that is an unstable system. Never coming back. Just let it go. Let the storm rage. Okay. Another way to think about this, I will not sing for you guys. But I just saw, what's her name? Azina Mendez?
Idina Menzel.
Adina Menzel. Anyways, I just saw, so my wife, we have this agreement where she will not play Christmas music before Thanksgiving in my presence. And then once Thanksgiving happens, she has open season on us. So she was playing Christmas music on Pandora, and then Idina Menzel song came on. Hey Scott. So these are another representation of a state. So these are called actually phase space or state space. Okay. And we can actually, this is a really useful way of looking at a state or a system in terms of its state space or its phase space. So you can actually plot what happens to each of its state variables over time versus each other. But so time isn't explicitly in the plot, okay? So say you had in this example, two state variables. You could plot them versus each other. So x1 is the first state variable, x2 is the second state variable. You can plot how they evolve in time, where time is implicit in this graph. So say you took a system that had an equilibrium here at the center, okay, and you perturbed it out here, and you let it go, and you see how it responded. What you see is that x1 will oscillate back and forth a little bit, and x2 will also oscillate back and forth a little bit. And together, when they oscillate back and forth, what they do is they create this sort of spiral inwards, and they approach the equilibrium value. And that is an asymptotically stable system looked at in phase space. So time is implicit sort of along the line here, time. Has anybody seen a plot like this? They're called parametric plots.
Yes.
Yeah. So, I mean, it should be familiar to you. I think that you do them in calculus.
Yeah, like
Diffie Q.
cats and squirrels.
Oh, yeah.
How the population changes, and it's like both axes of different animals, and time goes along with.
Yeah. Sources and things. Yeah. Absolutely.
What's the one with all like the dashed lines that like, what are those?
Fractals.
That's a different way of doing it.
Those are vectors.
Oh.
Vector
Vector space. No, it's
Vectors?
vector graphs or something like that with all the lines. Arrows?
Oh, the arrows. Yeah.
No, it's like something portrait. It's like it shows the slope of
Yeah.
whatever vector field it is at any given
Yeah.
point.
Yeah, that's it.
Exactly.
Vector field.
Yeah, they call it a.
Phase
Ooh.
portrait.
Well, phase portrait is There's a specific name for that type of plot though, but I can't remember what it is. But yeah, it's like this plots all of the directions of the vector field. Yeah, it's pretty cool. Yeah.
Slope field.
Slope field.
There's no.
I believe
there's
it.
Two different.
Okay, so pretty cool. A marginally stable system. Say that same system was marginally stable. We started it out at the same position. What it would do, potentially, this would be an example of a marginally stable system, it might just go in a circle in phase space and just never go off to infinity or never go to the equilibrium value. So that would be a marginally stable system. An unstable system would, for instance, would start to diverge, would start here and circle outwards. So that would be an unstable system. So that's this. We're going to talk a lot about stability in system dynamics next semester, but for now, we just want to have a little bit of an understanding of what it means for a system to be stable or unstable. And I hope that is clear from this. So these lines of how the state traces out in phase space through time is called a trajectory. Okay. All right. So that's really all we're going to do for stability for this semester, but I think it's important to take a look at that at least.